Welcome back, everybody. In this video, we'll be working on the beginning of section 10.2, which is about the hyperbola, the second of our conic sections that we're going to consider. In the last video, we looked at circles and ellipses, and here we're going to be looking at the hyperbola. So the structure basically is to look at just what a hyperbola is, and then the equations of hyperbolas and all of the different facts you need to know about that. And then how do you graph a hyperbola given its equation, and then how do you find the equation of a hyperbola given some information about the hyperbola. So that's where this is going. So first thing to do is just look at what a hyperbola is. In terms of a section of cones, remember we'd had this structure that was two right circular cones pointed basically what's you could think of as nose to nose. If you form the intersection or cross section or section of this cone structure with a plane as shown in the picture here, you end up with a hyperbola. A hyperbola is different from an ellipse or a circle in one big way, and that is that it is two separate pieces. So the graphs here will be two separate pieces. They kind of resemble each branch, what's called a branch of a hyperbola, resembles a parabola in a way, but the curvatures are kind of different. Some terminology first. So what you're seeing here in the picture, there's a lot to this. So the hyperbola itself is this graph kind of coming out in yellow highlight right now that was originally blue. That's the actual hyperbola itself. And this one, it opens, one branch of it opens to the left, one branch of it opens to the right. The hyperbola here is centered at the origin, so it's got a center right here at the origin, and then we have some other kind of important features for it. Provided this thing is centered at the origin, where the graph crosses the x-axis in this picture is the vertex, or vertices. There's two of them. Just like in an ellipse, there are two vertices, and where they were the endpoints of the major axis on an ellipse, the two vertices on a hyperbola are the 2 points where the hyperbola itself crosses the coordinate axis. There's also a co-vertex, or two co-vertices that appear here and here at the top and bottom of this picture, and those are not actually on the hyperbola itself. They form part of what's called a central box, which we'll talk about after a bit, that is kind of shown here in kind of green outline. Okay, the other structure that you're going to see on here is a couple of asymptotes. And then you have some experience looking at asymptotes in the past. This shape has some. Also, there are two asymptotes. And basically the deal is the graph gets arbitrarily close to each of the asymptotes as x increases or decreases without bound. So the two asymptotes are, of course, two straight lines. The graph of the hyperbola itself gets really close to the graph of the asymptotes as x either goes towards negative infinity or towards positive infinity. The two asymptotes intersect at the center of the hyperbola. Notice that the hyperbola itself does not pass through its center. Okay, here it's centered at the origin, but the hyperbola itself, again, is only these two kind of branches that open sideways. Okay, so you'll get more familiar with that as we proceed. We're going to take a look next at the equations for a hyperbola. So we saw with the ellipse that there were two equations depending on basically whether or not the ellipse was taller than it was wide or wider than it is tall. It turns out that there's two versions of an equation of a hyperbola, and they look basically like this: x squared over a squared minus y squared over b squared equals 1. Or x squared over b squared minus y squared over a squared equals 1. So they bear a big resemblance to the ellipse equation of they're set equal to 1. You have an x squared and a y squared in the top. You have an a squared and a b squared in the bottom. The huge difference here between hyperbolas and ellipses is that the hyperbolas have a minus, where the ellipse had a sum in between. And that comes from how the hyperbola is defined in terms of distances. we saw the ellipse was defined in such a way that the distance from a focus to the ellipse plus the distance from the other focus to that same point on the ellipse, that is a constant. For a hyperbola, it's a similar thinking in terms of distances, but this time the difference of the two distances has to be constant. So what's shown in the picture here are there's two foci, right? Foci, one at negative C0 and one at C0. The distance from negative C0 to the point XY on the hyperbola, that distance D2 minus the distance from XY to the other focus, or C0, that difference is going to be constant. So instead of having the sum be a constant, the difference is a constant, and that leads us to a hyperbola. Just as with ellipses, there are two foci as well, as we'll see in the equation. So we're going to end up with two equations depending on whether the a squared is under the y term or the x term, and that influences whether the hyperbola opens sideways, as this picture does, or whether maybe it opens up and down. Okay, so a little definition, we said this already, but worth repeating. A hyperbola is a set of all points in the plane, the difference of whose distances from two fixed points f1 and f2 is a constant. Those two fixed points f1 and f2 are called the foci of the hyperbola. Okay, so this table that you're seeing next is going to be important. You're going to need to know basically all of this stuff to do well in the rest of this section. But there's a lot here, so we want to try to break it down as well as we can. So there are basically two equations for a hyperbola. There's x squared over a squared minus y squared over b squared equals 1, which is this one. And then one that looks really similar, only it's y squared over a squared minus x squared over b squared equals 1. Or looked at another way, in the one on the left, the coefficient of x squared is positive, and in the other one, the coefficient of x squared is negative. Okay, so there's two different equations. We're going to work our way basically down and then across. Okay, so for the first one, we have x squared over a squared minus y squared over b squared equals 1. So for this one, it's going to be side opening, okay, rather than up-down opening. That's the one on the left. Okay, there are two vertices, and those will occur at plus or minus a 0. Okay, so how to see that, first of all, that this is going to be one that is side opening, and the fact about the vertices is just to think about intercepts. Okay, when you have a y-intercept, let's think y-intercept for a second. When you have a y-intercept, what's 0? When you have a y-intercept, the x's are equal to 0, right? If you have it's always the opposite of the name, right? So if it's a y-intercept, the x is 0. In this equation, going in here, in this equation, if x is 0, okay, then the whole left term is 0, and you have minus y squared over b squared equals 1, or you'd have y squared equals minus b squared. And so here, y would need to be complex. That is involving i's and things, square root of -1 and so forth. So what that means as far as our picture goes is that there are no y-intercepts. And as you can see here on the picture, when x is 0, the graph, here shown in red, the graph does not cross the y-axis. Okay, that's if we want to start thinking about y-intercepts. If instead you want to think about x-intercepts, okay, for an x-intercept, you have y equal to 0, right? Okay. So if instead we have y equaling 0, we'd have x squared over a squared minus 0 squared over b squared equal 1. And so we'll have x squared over a squared equaling 1. So x squared equals a squared. So x has to equal plus or minus a when y is equal to 0. And so that corresponds to these points where the vertices are, okay? And as far as the graph goes, they're at minus A0 and A0. Okay. The transverse axis is the length of the segment that joins the two vertices. Okay, the segment that joined the major axis, or that joined the two vertices in an ellipse, was called the major axis. The segment that joins the vertices in a hyperbola is called its transverse axis. Okay. And if it's side opening, as this hyperbola is, it's going to be horizontal and have length 2a. We're going to skip over the asymptotes and come back to that, okay? Formula for the foci, okay? We had a formula for the foci on an ellipse. We saw that it was c squared is a squared minus b squared, right? On a hyperbola, it's a similar look, but it's a squared plus b squared. Okay, how to keep that straight? For an ellipse, the equation for an ellipse had a plus in it, right? The equation for an ellipse has a plus in it, so the formula for the foci has a minus, okay? For a hyperbola, the equations for a hyperbola have a minus in them. The formula for the foci is going to have a plus in it. So it's always basically the sign is opposite the sign that you see in the equation for the function or for the shape itself. Okay. All right. We'll come back to asymptotes after a bit. Okay. And so that's what we've got. The transverse axis passed through the hyperbola itself. The other axis is called the conjugate axis. Okay, so there's some of the basic pieces of it. I wanted to do one example where we do a graph before we come back and talk about asymptotes a little bit. Okay, so let's see about a graph, and then we'll talk about asymptotes. Okay, so there's kind of a outline for this. You can sketch the central box for the hyperbola. That is going to be a rectangle. For now, it'll be centered at the origin. With sides parallel to the coordinate axes. One crosses at plus or minus a, one crosses at plus or minus b. The asymptotes go through the corners of the box. So let's first try this. Okay, let me draw that box on here. So on this, notice that I don't really need to care about whether this is x squared over a squared or is the a underneath the y or anything like that. For this, I need to know which way the central box is oriented. Or we can use the intercepts as well. So we'll see both ways. Let's start actually with the intercepts. That will be fun. So for this one, we want to think is when y is equal to 0, what do we get? If y is equal to 0 in the equation, we'll have x squared over 1 minus 0 squared over 4 equals 1. So x squared will equal 1. X will equal plus or minus 1. Okay. So x is plus or minus 1. Okay, and notice that that is the square roots of 1 are the denominator on our x term. If you take a look at the y term, the denominator for the y term is 4. The square roots of 4 are 2 and negative 2. So go up to 0, 2 and down to 0, negative 2. What you want to do is draw a rectangle that has those 4 dots on it. Centered at the origin, it's going to be from -1 to 1 in the x direction, and then from -2 to 2 in the y direction. That's what is meant by central box. Okay, and then the central box gives us a way to kind of figure out where the asymptotes are going to have to go. They are going to go through the corners of the box. So let's go ahead and draw that on. So a ruler will help you here. Okay, there's one. And then let's put on another one. All right, so then that's going to be the two asymptotes. So then we need to just figure out, is this thing going to be side opening or up down opening? And we saw that the intercepts were going to be a plus or minus 1, 0, right? So the two vertices are a negative 1, 0 and 1, 0. So then from there, basically you want to just kind of draw the curve so that it goes out towards the asymptotes. Okay, so there's that. We weren't asked to find the foci, but it'll be fun. Let's just go ahead and do that. So for the foci, that's c squared. And then you have to think, is it a squared minus b squared or a squared plus b squared? And the answer there is it's opposite the sign on the formula for the conics itself. So on a hyperbola, it's a minus in the equation. So this will be a squared plus b squared. So our two denominators here are 1 and 4. So 1 plus 4, that's 5. So c will be the square root of 5. Okay, c squared is 5, so c is square root of 5. All right, and so then remember that the foci have to lie along the transverse axis. So that means that they're going to have a y-coordinate of 0. So negative square root 5, 0, and square root 5, 0. That will be the two foci. Okay, the square root 5 is like 2 point something, right? So let me go ahead and draw those out there. All right, so there's the two foci kind of shown in blue. Okay, so then asymptotes. And we want to tie this back to that big blue table that we saw. The asymptotes here pass through the origin. So think about it for a second. So these are equations of lines that pass through the origin. So an equation of a line looks like y equals mx plus b. Okay, these pass through the origin. So that means that their y-intercept is 0. So they're going to look like y equals mx because there's no plus anything, right? So y equals mx. So really all you need to know is the slope. Here's how to figure out the slope. Let's take a look at the one that we did. I'm going to take the one on the right first, or the one that points from the lower left to the upper right. This one, it starts at the origin, and then it passes through the point 1, 2. Okay, so for a x change of 1, there is a y change of 2. So the change of y over the change in x, the change in y is 2, and the change in x is 1. Okay, for the other one, if we started at the point negative 1, 2, and go down to the origin, it will be down 2, and then right 1. So the two slopes are 2 and negative 2. Okay, confirm to yourself that those are in fact the slopes. Okay, so the two asymptotes, if we want the equations of the asymptotes, are going to be y equals minus 2x and y equals 2x. Okay, how can you get that off the formula without having to draw that central box? Okay, let's take a look at the original equation for our hyperbola, which is right there. Okay, the formula for slope that you learned like in beginning algebra here is m equals y2 minus y1 over x2 minus x1. That's the formula for slope, right? The change in y divided by the change in x. Okay, take a look at the denominator for y. That's 4. Square root of 4 is 2. Okay, take a look at the denominator for x, 1. Square root of 1 is 1. So the two slopes are plus and minus, because there's two of them, plus and minus 2 over 1. The square root of the denominator on y divided by the square root of the denominator on x. Okay, that's what you see here on that blue table or chart that we had. The equations for the asymptotes are y equals plus or minus b over ax, or plus or minus a over bx. You don't want to sit down and memorize this. I think it's a waste of time. Instead, what you want to know is this. Okay, for the first equation, you'll notice that the denominator for y has a b in it. Okay, b is on top on the slope. The denominator for x has an a squared in it. Here, the denominator has an a. So it's basically the y number divided by the x number. Okay. For the other one, the denominator on y is a squared. This has an a on top. Here, the denominator for x has a b squared. It has a b on the bottom. So regardless of what you're calling the a and the b, because it doesn't really matter, you're going to, for the equation of the asymptotes, you're going to have the square root of whatever's under the y on top of the square root of whatever's under the x. Okay, another example is going to make that a little clearer. So we will do that. Okay, right here. So we're going to sketch the graph of this hyperbola as y squared minus x squared over 9 equals 1. We're going to find the vertices, the foci, the lengths of the transverse axis, and also the asymptotes. Okay, so go ahead and get started on that, and then we'll work on it together. All right, so let's get started on this. So we're going to start by figuring out where the vertices are. This one is centered at the origin. All of these will be, for the time being, centered at the origin, so we want to figure out where the vertices will be. So let's take a look at our equation. We have y squared minus x squared over 9 equals 1. So to figure out intercepts, we need to think about whether x or y is equal to 1, right? Or equal to 0, I'm sorry. And then what is the corresponding y? So for this one, let's try y equaling 0. Okay, if y were 0, what would we get? We'd have 0 squared minus x squared over 9 equals 1. We'd have negative x squared over 9 equals positive 1. So that would mean, right, that negative x squared would have to be 9, or x squared would have to be negative 9. That would mean that x had to be complex. And so we're not going to have y equaling 0. So this one won't have any x-intercepts. Instead, let's try x equaling 0. Okay, if x is 0, we'll have y squared minus 0 squared over 9, and that's equal to 1. We'll have y squared equals 1, so y equals plus or minus 1. So when x is 0, y will be plus or minus 1. Okay, so that will be our vertices. We know that this doesn't intersect the x-axis, and so it's going to not have any x-intercepts. So I know roughly it's going to have to do that, basically open up and down, but we'll make a better looking picture. But that's what we've got so far just by trying to figure out intercepts. So the next thing I'm going to do is think about asymptotes. So to do that, rather than trying to draw in that central box, let's take a look at the denominators that we have in our equation. Okay, so for asymptotes, here, this is, let's do it down here. So we want the asymptotes. Okay, our equation was y squared minus x squared over 9 equals 1. Okay, so now I know that the formula for the asymptotes will be y equals plus or minus. There's two of them. There's one that's positively sloped and one negatively sloped. And so it will be the y equals mx plus b, right, for equation of a line, but there's no b because it passes through the origin. So really all you need to know is the slope. Okay, y equals something x. Okay, the slope is always a y change over an x change. What's the denominator on y squared? Okay, it's like y squared over 1, right? So that's like y squared over 1. So the square root of 1 is 1, and so we're going to have a 1 in the numerator. Okay, x squared, right? Slope is change in y over change in x. So the bottom is going to be the x number. Taking a look at the denominator on x squared, that's a 9. Square root of 9 is 3. So the two lines will have slope plus or minus 1/3 x will be the equations of the lines. So from there, we can go ahead and draw in the asymptotes. So we'll do that, and then we'll have enough that we can draw out our hyperbola. So let me get a second point. We know they're going to pass through the origin. I know the slope is 1/3 for the first one, so I'll go up 1 and right 3. And then for the other one, I know it will be down 1 and right 3. Okay, so that will be our where our asymptotes will go. All right, so let's go ahead and draw those on. Okay, all right, so let's check if they should pass through the origin, right? Okay, good. All right, so now we're ready to draw on our hyperbola. If you want, you can calculate some extra points and plot those, or it's probably sufficient to just kind of freehand sketch the hyperbola outwards. So your graph should show that the hyperbola is getting closer and closer to those asymptotes as x increases or decreases without bound. All right, so we got our graph. Let's make sure that we've gotten everything. So we've got the vertices. Let me put the vertices labels on the graph. So that will be 0, 1, and 0, -1 for the two vertices. Okay, I didn't get the foci. We're going to have to get that. The length of the transverse axis. The length of the transverse axis is basically the distance between the two vertices. So from 0, 1 to 0, -1 is a distance of 2. And then we got the equations of the asymptotes already. So the only other thing that we need to get is those foci. So let's do that. C squared equals A squared B squared, plus or minus in the middle. Okay, on a hyperbola, the equation has a minus in it. So the formula that it relates the C, A, and B will have a plus. Okay, our denominators here were 1 and 9. Note that since we're adding, it doesn't matter which one was the A and which one's the B, because C squared is going to equal 10 no matter what. So C is square root 10. Okay, so now you got to ask yourself, okay, is it going to be root 10 0, or is it going to be 0 root 10? Okay, so remember that the foci are going to lie along the transverse axis for the hyperbola. In other words, they'll be along the same axis as the vertices are. So that's the y-axis for our picture. And so that means the x-coordinate has to be 0. So we'll have 0 root 10 and 0 negative root 10 for our foci. Okay. All right, so that does that example. We got everything, all the pieces. Okay, so what we're going to do next is take a look at how you can kind of arrive at those equations of asymptotes. When we looked at the equation of the ellipse, we saw that there was kind of a lengthy algebraic procedure to find that. There's also a similar lengthy algebraic procedure to find the formulas for the hyperbolas. Those are in the book, and you can look at that if you like, but we're just going to proceed with it. This part involving deriving the asymptotes for a hyperbola does take a few steps in algebra, but I think it is worthwhile for us to see this. It won't be as long as the equation of the ellipse, though. Okay, so we're going to do the derivation of the asymptote equations for this side opening hyperbola. So the equation is x squared over a squared minus y squared over b squared equals 1. So you can see by taking a look at the equation, if y were equal to 0, x would have to be plus or minus a, right? Because we'd have x squared over a squared equals 1. So we'd have x squared equals a squared. Okay, if y were 0. So that accounts for why the vertices are right there. So this equation is appropriate for a side opening hyperbola. All right, so we want to take this equation for the hyperbola and solve it for y. So what we'll do, where we'll start, is we'll take this equation, we're going to multiply both sides by a squared b squared. So this will take a few steps to do, but they're going to be good. So we're going to multiply both sides by a squared b squared. Okay, and the reason for doing that is just so that we can eliminate those denominators on the left-hand side. Okay, so we'll have x squared b squared minus y squared a squared. You can alphabetize those if you want, I don't really care. So there's a squared b squared on the right side. So now we got rid of those fractions. Now we want to get y alone. So our equation so far has 1, 2, 3 terms in it. Some have y's, some don't. There's actually one that has a y in it, only the one that I've labeled 2 here. So I'm going to put that one over on the right side, and then I'll bring 3 over to the left side. So I'm going to be swapping terms 2 and 3 in the next line. So we'll have x squared b squared minus a squared b squared equals y squared a squared. Okay, our goal here is to get y by itself. We're trying to solve for y, okay? As far as why we're doing that, we'll see when we get to the end. But essentially, we are thinking about the asymptotes, which is we want to know about the end behavior for this graph. And so what is happening to y as x gets big? That's where we want to know y. All right, so now I've got still 3 terms. The one that has a y in it is on the right side. The 2 terms on the left don't have a y. So we're going to go through next and divide both sides by a squared. So we'll have y squared is equal to x squared b squared over a squared minus b squared. Okay. All right, and so now we're going to take the square root of both sides. So y will equal plus or minus. We'll have the square root of x squared b squared over a squared minus this one will make that a squared b squared over a squared. I kind of canceled that a prematurely, so I'm going to want to get that subtraction done. So we're going to keep that denominator in there. All right, so we're not quite done with this yet. I'll make sure that you can follow all the steps in there as we proceed. All right, so now we want to continue rewriting this a little bit. So what we're going to do next is we got a common denominator for our 2 fractions, so we will go ahead and subtract. We'll have x squared b squared minus a squared b squared, and that's over a squared, and we're taking the square root of it, and that's y equals plus or minus that radical. Okay, continuing onward, we'll factor the b squared out of the numerator, so we'll have plus or minus square root b squared over a squared, and then what's left in the top is x squared minus a squared. Okay, so now the b squared over a squared that we have on the left, we're going to take the square root of that part. And normally taking square root of b squared over a squared, we would need a plus minus, but we already have a plus minus symbol on here, so we don't need to add a second plus minus on there. So then we'll have y equals plus or minus b over a, now it's starting to look familiar, square root of x squared minus a squared. Okay. All right, so what we're going to do next is kind of an interesting device that shows up a lot the further that you go into math. We're going to multiply by a factor of 1, and it's going to take this special format of being x squared over x squared. Let me make that a more contrasting color. All right, so x squared over x squared is equal to 1. And in case you're concerned about division by 0, let's just say that x is not 1. We're, after all, interested in the end behavior for this graph, and so x is pretty far away from 0. All right, so we've multiplied through here by x squared over x squared, and so that didn't change the value of what we're working with any. I'm going to take the numerator x squared and bring it outside the radical, okay? The square root of x squared will be an x. So we're going to have y equals plus or minus b over ax. That really looks familiar. And then inside, we'll have x squared minus a squared, and then that whole thing will be over x squared. Okay, we're almost there. All we have to do really is show that this radical is pretty close to 1 in the end. So I'm going to separate that radicand into two separate terms. We'll have y equals plus or minus b over ax square root. And then we'll have x squared over x squared minus a squared over x squared. Okay, so now the thing is, this is the part where we need a little more thinking. X squared over x squared is 1, right? And then a is a fixed constant. It just came from the equation of our hyperbola. A is a constant, and so x is getting larger and larger and larger. So this part, a squared over x squared, is getting close to 0 as x gets towards plus or minus infinity. So overall, this radical is approaching 1. And so in the end, we end up with, if the radical is nearly 1, what's left, it's multiplied by plus or minus b over ax, we're going to end up with y equals plus or minus b over ax. And that's where the equations on those asymptotes come from. If you didn't follow all the algebra here, that's okay. This is not something that you're going to need to reproduce for this class, although it is built out of stuff that you do know how to do. If you are going to end up taking calculus one day, then the kind of thinking that was involved there at the end about what happens if x is really large, that kind of thinking is going to be useful when you go on to take calculus, if you do. Otherwise, you mainly will just need, for this class at least, what those equations for those asymptotes are. All right, that takes us to the end of this video. It doesn't finish up section 10.2 for us, but it does take us to the end of this video. So in the next video, we'll continue with a couple of more examples, and we'll start working on building up the equations for hyperbolas given some information. In the meantime, let me know if you have any questions, and have a great day.